Hi, this is Mrs. Jackson. This is Chapter 3, Section 5, Part 3. In this last video, we are going to practice using the binomial theorem to expand a binomial. Okay, so the purpose of the binomial theorem is to be able to raise a binomial to a higher power. In this case, we have a power of 7, and to find the equivalent expression quickly and efficiently using Pascal's triangle. If you recall, in the previous video, we looked at that binomial theorem, and we called the first term a, so in this case our a equals x, and we called the second term b. So in this case, because we have minus 1, we're going to call our second term negative 1, and we have the coefficients in front of each of the terms as the a term is stepping down. It starts out at the maximum exponent and then it increments down, while the b term is starting at the minimum exponent and stepping up to the maximum. So if we look at what this might look like, we are going to rewrite this as the initial coefficient with the a term raised to the highest power. In this case, it's going to be 7. And the b term is not in this first term because b is actually raised to a power of 0. So anything raised to a power of 0 is equivalent to the number 1. That's why it's not in this term. So then we're going to step to the second term. So we have the coefficient sub 1. A is going to start to increment down, and b comes in. So now b is raised to a power of 1. Then we've got our coefficient sub 2. A steps down to 5, and b steps up to 2. And we've got coefficient sub 3. A is stepping down to 4, while b is stepping up to 3. And so on and so forth. A is continuing to step down 1 increment, while b is stepping up 1. I'm going to move the window over here. And we've got each term coming in until we either decrease all the way down or increase all the way up, and increase all the way up, I should say. So now a is down to a power of 1, b is up to a power of 6, and the last term is c sub 7. A is at a power of 0, so we're not going to see that. That's the number 1. And finally, b steps up all the way to 7. Okay, now we need to substitute in our coefficients as well as our terms, a and b, and then simplify. In order to find those coefficients, as you know, we need to refer to the Pascal's triangle. I think I'm going to fit that down here. We need to go to row 7 because our exponent is 7. And so I start out as 1, and the next row is 1, 1. The next row is 1, 2, 1. The next row is 1, 3, 3, 1. The next row is 1, 4, 6, 4, 1. The next row is 1, 5, 10, 10, 5, 1, 1, 6, 15, 20, 15, 6, and 1. Let's count our rows here. We've got row 0. Remember, the first one is 0. 1, 2, 3, 4, 5, 6. We need one more row. So we've got 1, 7, 21, 35, 35, 21, 7, 1. So this is our row that we want, and these are our coefficients. So this is c sub 0, c sub 1, c sub 2, c sub 3, etc. And we're going to substitute those in to our formula above, as well as our values for a and b. Okay, so we can start our substitution process. C sub 0 is 1, of course, so I could just leave that out. And a is x, so that first term is x to the 7th power. C sub 1 is 7, and a is x, so x to the 6th power, times b, which is a negative 1. C sub 2 is 21, x to the 5th, times negative 1 squared. C sub 3 is 35, times x to the 4th, times negative 1 cubed. C sub 4 is also 35. And C sub 5 is 21. So I'm just substituting in these values, and then we're going to simplify as our last step. C sub 6 is 7. This is a negative 1. And C sub 7 is 1. And our last term is negative 1 to the 7th power. And now the only thing we have to do to find the expansion of this binomial is just simplify. So we've got here a negative 1 multiplying by a positive 7. So that's just going to turn that sign into subtraction. And negative 1 squared is positive 6. It doesn't look much like a 6. So this is going to stay addition. And negative 1 cubed is negative, so this is going to turn the addition into subtraction. Negative 1 to a power of 4 is positive 1, so this stays addition. And so on. So the odd powers are going to change the operation from addition to subtraction, while the even powers are going to keep with addition. Okay, let's try another example that's a bit more algebraic. So in this example here, I have my a term equals 2c, and my b term just equals d, and my n equals 6. I'm going to cheat over here and use the same Pascal's triangle that we already drew, so I can see that C sub 0 equals 1, C sub 1 equals 6, C sub 2 equals 15, C sub 3 equals 20, C sub 4 equals 15, C sub 5 equals 6, and C sub 6 equals 1. So if I were to expand this, again, we're going to start out with C sub 0 times our first term, a, raised to the highest power, so that's going to be 6, times the b term raised to 0, which reduces to 1. C sub 1, a is going to step down while b comes in. So a's exponent is stepping down while b's exponent is stepping up. And you can see the pattern. And b goes all the way up to 6 there, while a is down to an exponent of 0. So it just drops out. And now we're going to start to substitute. So I've got c sub 0 is 1. A is 2c, and the whole expression there is going to see that power of 6. C sub 1 is 6. I'm just substituting in now d for b. And I'm sorry, I'm having to write really small to fit everything in. So everywhere I see an A, I'm substituting in 2C. And everywhere I see B, I'm substituting in D. And I could just drop the C6 as just 1. All right, so now when we do our simplification, we do have to follow order of operations. So we have to do the exponents before multiplication. 2 raised to the 6th power is 64. 2 raised to the 5th power is 32, and 32 times 6 is 192. 2 raised to the 4th power is 16. 16 times 15 is 240. 2 cubed is 8. 8 times 20 is 160. 2 squared is 4. 4 times 15 is 60. And 2 times 6 is 12. And there we have it. If we were to do these binomial expansions by hand using the box method, we'd need a lot of paper and a lot of time. So hopefully I've proved to you that this theorem is worthwhile and it's a time saver. Thanks for listening. Hope this helps.